I'm working with the enterprise customer mostly, and yeah, happy to share with you today the our findings on how to architect, design data-intensive workloads. And what we are going to go over today is, first we will try to understand the role of the databases and maybe data stores in general into modern application. So we have a new pattern of building applications, regardless actually of the programming language, but especially also for Java. And the way we design data-intensive application and how we store the data afterwards and process it has its own challenges, right? So we were going to look at some data dimensions to consider when we design these data stores. And then with any design, of course, there are some trade-offs to balance, and this is what we're going to do next. And after all this technical, we're going to go to practical. We're going to go over a use case scenario where we try to design an application from scratch, and then go over some iterations and see how we progress through our data modeling and data design for the application. Great. So if we take a look back into the time, I mean, in the 60s and 70s, most of the developers, they only knew mainframe. That was the most predominant way of building application, which was quite simple, right? So we just put everything in one server. There's no dependency. There's no distributed actions to be done. It was quite simple. They had, of course, also big challenge, which is the scalability and maintainability of software. So what we did afterwards, mostly into the 90s, we said we want to disconnect the data store from the application, right? So we took the database out and we built more like a client server application model, which came also with challenges of not scaling and not being so maintainable through different, let's say, domains of application. Then we said, no problem, we're going to have a free tier application. We take out the presentation part, we abstract it away. We have the business logic in our backend, and we have our database that has everything behind the scenes. And this really works even today for most of the application, right? So, but at some point we are hitting limits. We are hitting limits in terms of scalability, hitting limits in terms of how we collaborate together on the common software. So we moved step by step more to microservices late. I mean, at least in the last 10 years, it was the mainstream adoption of microservices was really high. And this actually implies that a modern application running on microservices has some other requirements as we had like 20, 30 years ago, right? So we're not thinking anymore in just delivering an application. We need to deliver it with better performance, scalability almost unlimited, and availability to up to 100%. And all these challenges come actually in all the domains. I mean, if you look in e-commerce, in media streaming, in shared economy, or everywhere, if you want to share something or lease something, everything goes to more and more scale, more devices, more requests per second. And this is a challenge actually today, because in development, we are trying to do a shift in mindset, but still our traditional web server free tier application is still there. So still a lot of enterprise customer, even older customers, that still have working environments that have free tier application, and developers are trying to model that to make them more, let's say, more modern in terms of more scalable and more maintainable at the end. So there's a move now from traditional to microservice to decouple architecture, right? So we still pretend those three layers for presentation, business logic, and data, but now we take also domain-driven design, and we implement domain-driven applications which are loosely coupled, and we speak with each other more between domains. We speak with events and not direct calls. And a shift into that area is happening lately also in the data layer, right? So at the beginning, if you remember, we moved to microservices, but all the microservices were still writing in the same database, was not really a domain-driven design there. But now lately, the developers really have the power now to choose their data stores behind the scenes, right? So they have the power now to say, hey, I want from this application a NoSQL database. For another application, I want a graph database. And this power came actually with the cloud and with the managed services offered by the cloud providers. And flexibility and, let's say, this choice comes also with a responsibility at the end, right? So if we do design and choose another database, like a normal relational database, then we need to do our homework and look on how to design that to really scale and be highly available for our application. So that's the challenge today. This is what we are facing as developers, as architects. And if we took another idea, I mean, Robert C. Martin said like 10, 20 years ago already, databases are dependency in an application, but the core of the application is all about entities and use cases, right? So we are building the application business rules in the center with the entities. And what we are doing afterwards, once we understand which business rules we need to implement, which enterprise entities we have there, then we add on top of that, we add, for instance, new presenters. So we add new interfaces that use the core business application. We add gateways, and here comes also the databases, right? So databases and data stores are kind of details in this clean architecture that is presented. And what I really want to encourage you also to think also as in this mode, right? So databases and web are details. We are focusing on the core business application rules. And then afterwards, once we understand those requirements, we can choose our data store accordingly with our requirements. So keep your model still independent of technology. And if we look at some steps, how you can do that, and these steps may seem that are old. I mean, the step of defining a data model is still looking down and writing application requirements. It's still defining an entity relation diagram. As why do I need an entity relation diagram? You need that as a part of a development process, because you need to know how your entities relate to each other and which dependencies are there. How you model that will go afterwards into the next section, and you need to write down your data access. So you need to write down how do you access those entity relationship, so entities, and what are the relation between them to satisfy those data access patterns. And then you model your primary key, your sort key, and your secondary patterns, right? And once you have that, you need to experiment to do some optimization as needed for your application. So until the last step, you can actually build your application just with plain file, right? Just a JSON file. You can mock it at the end, right? And then once you go more into production, or to, let's say, to integration, to production stages, then you should choose a data store that should satisfy your requirements. It may need that you maybe need transaction support, right? So, or maybe you need to be very fast in inserting. So you need low latency by inserting. So all these requirements will lead you to implementation of that gateway to a data store. And we did that. So I personally did that, had the chance to do with many companies. And what is surprisingly is most of the customer that I had, they still think in, let's choose the best and ideal database that you have in the cloud, right? So they all want innovation and agility, should have ACID transactions, strong consistency support. We want a database which is just limitless, scalable, and it's highly performant regardless of query complexity. It needs to be highly available, simple to use, cost effective. So all these requirements kind of come out from the analysis on the application. And I'm really happy to say that this does not exist. So such a ideal database, it's let's say it's not according to physics rule, right? So the rules of physics said you cannot really have everything in one place and still have it cost effective. So what we need to do is we need to look at our application, actually choose the best data store that we have out there, and accept some trade-offs that data store is bringing into our application that we can work with, right? So find the sweet spot for your application. And there are some ways you can do that. So the first thing that we want to look at and how to choose that data store after we did our homework, looking at the application requirements, is looking at the dimensions, right? So one of the dimensions to consider when you do data modeling and choosing a data store is the shape of the data, right? So this is not something new. Shape of the data has been out there since many, many years. Now we do have technology to match the different shapes of the data. That's the difference. And then we look at the size. So how much data do I really need in one query? So, or how many inserts do I do per second, right? So this sizing and scaling will, it's a big factor actually in choosing the data store. And then we have the amount of compute that we need to do in the database. So pre-query and after query, right? So you can have super relational database that do a lot of computations, join averages, ranking, and things like that in the database already. So they prepare your data for you. Or you can have more like, let's say, NoSQL part where the data is already there. It's just going to be delivered to the application, and all the computation is happening actually at the application side to do different, I don't know, averages or searches or filters. So think about these three dimensions when you choose your data store. Now, there's some example, right? So if you look at the shape of the data, this is nothing new, right? So we have row store, column store, key value. So you need kind of to identify how is actually your data in the application presenting itself, right? This is more like, let's say it's a tracking application. So it's a low latency, which just comes one after the other. So you're getting data from an IoT device, for instance, or it's more like a relationship recommendation. Maybe it's a graph type shape of data, right? So looking at the shape of data is the first one. The second one is size and scaling. One of the things that you need to look at is size at limit. So think about your modeling an application, and you want to see how big this data can be in a table, right? So if you have number of countries or cities in your data, this is kind of bound, right? So we're not going to have tomorrow an additional 100 million cities into our database, right? So this is bounded data. But if you think about sensors, or you think about clicks in an application or something like that, this is quite unbounded. We can really have just overnight millions of new records in our database, right? So think bound, unbounded, how this will scale, how do you actually get that data? So working set size, how much data do I actually actively work with at a specific time or in a specific application session? And then is the compute flexibility. Like I said, think about how much computation you need to do in the database before presenting the data to the application, in comparison to how fast do I need the data in my application so I can do something with that afterwards. And then comes the decision, right? I'm pretty good in relational databases. I did it in my studies. So I don't know exactly what is NoSQL, so I'll just go with relational. And it will work. It will work for most of the cases that you just start with relational database. It's not something bad or outdated. It's still very used out there and still the most used pattern into data stores, because it provides a lot of flexibility, right? So you can really take those, we have like a booking application now. We can really take those 6 tables and do 1,000 types of query on top of that, right? This is quite flexible. The problem with that is when you have so much computation in your database, right? Because if you want to get a booking for a specific hotel room and an invoice, then you need to join like 5 tables. That's computation time, right? So every time when you need data from the database, it will just use CPU and memory again. And this can hit some limitation at some point in scalability. On the other hand, in NoSQL, you can have this data already pre-computed for you, right? So this join is not happening anymore. Now, if you work with relational databases, this looks like a materialized view, right? So we kind of created a materialized view. We store it as a JSON file, and then there's no computation in the database to be done. You just get it by key, for instance, and it works really fast. And there are advantages and disadvantages, and we need to understand that. So on one side, like I said, SQL is super good for structuring, for putting constraints, for putting transaction futures. So all these type of things. So optimize for storage, for instance, you don't have duplication of data in relational databases ideally. And it's awesome for all app use cases. So if you don't know the queries, or you have analytics queries that you don't really know, and you need that flexibility, awesome. Just go for a relational database. And it's going to be hard at some point in the future, maybe it will be years, until you will see the scaling will be a problem of latency. Partitioning, sharding of data is quite hard, because it's relational, right? So you have a lot of relations between those entities. It's quite hard to separate that into sharding data if you don't do it from the beginning. On the other side, NoSQL was invented, and it has a value because it's flexible, right? So you have a flexible schema. So you have schema on write, but it's optimized for computers. So you have a lot of duplication in your data, and that's okay. Right? So that's okay with that. Storage is cheap. You can shard data. There's not so many relations between those entities into the database. So it's easier to shard data. And it has almost infinite scaling, and it shines in OLTP use cases. So small, fast transaction, create, put, update, delete. So it is small. It just shines into that. But it's hard to design properly, and it's hard to do complex computation. It's not so easy to do some averages or things like that in a NoSQL database. So please be aware of those trade-offs when choosing. Now, if you look at those two, the difference between them, the main difference that I see between them is the scalability, right? So on one side, relational database will work awesome, flexible, but it's hard to scale. On the other side, we give this flexibility of query aside. So we trade off flexibility of query to do scaling and NoSQL database, right? And one thing that is important to understand is actually scaling a problem I need to solve? So do I have a scaling problem now in my application? And if I don't have a scaling problem now in my application, maybe I'm at the beginning or I have a greenfield project, when will scaling be a problem? So if you understand those inflection points, when is scaling actually a problem, then you can decide from the beginning, just go for a relational database. It's quite fast. It's nice to develop. You have enforced constraints directly into the database. And you need to know when the scaling of your application is going to suffer. And how you do that, you benchmark your application, right? You just start sending thousands, millions of transactions into your application as it is today, and look at if you add more and more CPUs, does the transaction per second increase linearly with those CPU? And you will see at some point will be an inflection points here. For instance, so if I had more than 50 CPUs to my database, for instance, or data store on my application, doesn't matter how many CPUs do I add afterwards, the transaction per second is not growing anymore, right? So it's still something is blocking there, so something is waiting. And I know, okay, if I approach like more than 300 transactions per second, that's my scalability limit of the current application. The same with hot data, queries per partition. You can look at your partitions. I mean, in relational database, partition could be directly only one table, one partition of that table. How hot it gets with the number of thousands and million transactions per second. So at some point you will see that some of the partition of the tables are really, really hot. So the blocks are maybe blocked a lot into the memory, and that's your scaling point of application. The same with lock contention. If you're doing transactions in your database, at some point, it doesn't really matter if you add more and more sessions or more transactions to your database, it will not scale let's say your transaction per second, because more sessions means more contention in application. So at some point, let's say another 300 for instance here, that's my scaling point that I need to, it's an indicator for me that I need to look into redesigning my application. And the same with the query latency, right? So if you had more and more sessions, the latency at some point will just gonna skyrocket, and you need to know where. So between 300 and 350 for me will be still okay, but afterwards I need to redesign my application. So first, understand if scaling is that problem. We can understand that by benchmarking our application in a safe environment to know when is actually the inflection points of my scaling. When you look at that scaling, and then I say, okay, so I have a problem with query latency, for instance. So I need to redesign my application, maybe choose another data store for that part of application to have more efficiency and low latency. And there is a theorem for that. So there's a pi theorem for data stores, where the theorem says between pattern flexibility, efficiency, low latency, and infinite scale, I can only choose 2 at the same time. So I cannot have all 3 at the same time. And if you look at data models, and if you look at for instance, what we have on AWS as managed databases, we can see that for pattern flexibility and infinite scale, there's the classical data warehouse, right? Or let's say data analytics query tools like Redshift and Athena. And those can really have a lot of flexibility, but it's not really low latency, right? Because it's still reading maybe in parallel at least, but it's not really low latency for infinite scale, for a query which is returning, for instance, millions of results. On the other hand, if I need pattern flexibility and low latency, it's still nice to have those relational databases, right? So think about RDS, think about Amazon Aurora. Even you can think about OpenSearch like a text search database, or a DocumentDB like a document database, or graph database. It still gets you low latency with pattern flexibility in one direction. So for instance, let's say in graph searching, but it's not going to scale infinitely, right? So you need to maybe break out your application in multiple domains to avoid that scaling problem. And if you really need low latency and infinite scale, but you kind of trade off the pattern flexibility, so you cannot just query whatever you want in that database, look at DynamoDB, right? Or Keyspaces, or just memory databases, which are super low latency, super fast, scale almost infinitely, but you cannot do many things flexible with them, right? So you have pattern flexibility for that. Great. These are some trade-offs that you need to consider there. And usually when we talk with customers, there's a kind of story that repeats itself, right? So people usually start with non-relational data interaction, right? So you have a relational database maybe it's already managed database out there. And what happens at some point, you say, for this part of the application, I may need to scale my reads. Maybe I'm reading a lot from the database and it costs me a lot of IOPS. So what I think, first thing, look into non-relational data interaction. You take a part of that application and kind of implement caching for that, right? So you take Elasticache maybe, or MemoryDB. You do those memory structure between the applications and the database itself, and you store everything in memory with a different algorithm. Every time when something gets read from the database, you can store it in cache. Second time that is read the same thing, and it's a match maybe on the SQL hash, then you just get it from the memory. So this is the first thing that people usually do when they look into NoSQL data interactions. Afterwards, maybe you have not only reads, but also writes. So you need to be faster in writes. So for instance, you have an application that sends a lot of data every second. So you need your writes to be low latency there. Then people look more into NoSQL databases like DynamoDB, like a key value persistent database. They look into DocumentDB databases. So, okay, then not only have those, like 5 tables and do join every time, but put it maybe in the document database, embed those 5 entities into one JSON, like parent-child relationship, and then you just get it with one query. And it works pretty nice for different use cases. And at some point, they realize maybe they have specialized, let's say, use cases. So you take part of that application and you say, maybe I want to do some graph and highly connected data on top of that. Maybe I want to do some recommendation, or maybe I want to do fraud detection and search similarities in a graph. Or I have a time series data set. So the data are coming with the timestamp, like sensors or tracking mechanisms, or maybe I put into a time series database, which is much better than a relation database for that specific use case. So this is the story, how usually it evolves. So you go to relational, and then you put cache, and then you look into NoSQL for part of the application. And then at the end, you look into those specialized use cases. But the idea behind this, there's no fixed database for everything, right? So you take different ones for different use case scenarios. So enough talking, let's look maybe into a use case. So I have an application, which is a hotel booking application. So think about a platform where there are managers of the hotels that put hotels and rooms and prices on one side, like the producers, and the consumers, they search on those hotels, rooms, and prices, and they try to book something for a specific date, right? So it's a classical hotel booking application. How do we start such an application as a developer, maybe together with architects, and say, let's write some user stories, right? So what needs to happen into our application? Maybe we have managers of the hotels, they are adding their hotels and their rooms and their prices, like photos and description of the rooms on one side. And then on the other side, we need a guest to search for those rooms. So we may need here management of the searching of those rooms for those guests. Maybe the guests start now a user story to book that room and pay for it. So we need that payment module for our guests, and maybe they receive some similar recommendations at the end. If you book this, maybe you are interested in that, or you may need a taxi or a flight for your booking. So you write your user stories. That will be the first step. Once you write the user stories, like we said in the beginning, we need to understand maybe what are our domains and entities, right? So we design some entities and we say, okay, for hotels, I need an entity for hotel. Into a hotel, I will have multiple rooms, so different types of rooms. And for each room in a hotel, I will have different pricing for different dates, right? So this is pretty straightforward, and the free entities. And then we do a search on top of that. And that search is used afterwards by the booking and billing and payment entities, right? So we may have a booking for a specific period, and you make a billing invoice for that, and there's a payment for that, right? Maybe you get some preference and recommendation afterwards. This is pretty simple. So iteration number 1, right? So we look at those and we say, I cannot really put everything in one database. So what I will do, I will just split in domains first to make it manageable. So it'll be like 3 teams having each of them one of the domains to manage and implement. And if you go a little deeper, so go into next iteration, we look at the pricing room hotel, right? So a search on top of the prices. What do I need that? So I need to see what's my data access pattern. So I'm looking into the data access pattern. I may need to do create, read, update, delete on room on hotel, right? Like create a room, get a room out, put a price, get a price out, reserve a price, right? So is it available or not available? These are really fast create, read, update, delete into room hotel key, in primary key. And then at some point, I will need all the available rooms in a hotel, all the prices in the room. Maybe I need to update the prices once someone books a room. I only have like only a couple of rooms, so maybe I increase the prices. And then you filter hotels on multiple attributes. So this is quite a lot of data access patterns inside. So I can really put that in a relational database design, right? It's super fast. I mean, I can do that in 1 hour, the design, and then we implement the user story in the next couple of sprints. And then we say, look, we have a booking. The left side, we have the relational entities between them. So every time when I do a booking or I search, I have this flexibility of just joining tables and querying them and do all kind of stuff. And then comes the idea, what will be some problems that I will hit at scale? So if my application really starts to scale now, if I have hundreds or thousands of transactions, what's the first thing that is gonna, let's say, will be the bottleneck, right? So the search is pretty flexible, but this search will not scale linearly, right? If I had more compute power, but I have a lot of transactions here happening, booking and pricing in rooms, this search was going to hit at some point some limits of the relational pattern, right? The price and updates are really hot objects. So once something books something, you need to update the price or maybe increase the other price of the room. So it's really dynamic hot objects there. And the joins at the end will do a lot of unnecessary compute if you have the search. So I already see like two patterns. At some point, it's going to get hot on the left side, right? So it is the rooms and the prices. It's a hot object there. Everybody wants to write there and read from there. And on the other side, the search needs to be flexible. So what am I going to do? Maybe I will take the chance to look at a possible other design, right? So I look at my domain and I see two patterns. On one side, I see get input prices. They're really fast OLTP transactions, right? It's short and low latency transaction, no complex queries. So I don't do reports on pricing or things like that now. On the other side, I need some flexibility on the search. Think about the search. It can search through hundreds of attributes of those hotels, right? But I don't really need transaction support in my search, right? It's more like latency is important, but not critical. You know, when you search from a hotel, it's like loading, like 5 seconds. It's okay, right? So it's not critical, the latency. So these are different requirements. So this is in the second iteration of our application, I decide to split that domain again into two because there are different requirements out there. So what I do now, I'm looking at the on the left side, for instance, for get input prices. So this is a classic OLTP application, really fast, low latency. DynamoDB may be a really good fit for that because it supports those writing and reads with low latency, and I need that. On the other side, for search, I can't really use DynamoDB because DynamoDB is not built for analytical and search queries. But what I can do, I can use like an open search service. This is like a text search on top of the data. So this means these two microservices, these two domains will need somehow to share data between each other. So a possible architecture afterwards could look something like this, right? So on the left side, I have my pricing. So over an API, I'm doing those create, read, update, delete to our prices and rooms. And I stream those changes to the other domain, maybe asynchronously over a breakpoint here, Lambda, into an open search index. And then if I'm searching for a specific, hotel, location, price, date, then a index search will be much faster than to search directly from Dynamo. So we are streaming those changes to OpenSearch. We do the search, and then afterwards we do the search. We can use other microservices, for instance, to do the booking itself, right? Like blocking the room and doing the payment for a specific room afterwards. Great. So this is how it looks like. This is the let's say the natural build and design process of designing such a data-intensive application. You start with a normal, maybe relational model, and then you find scalability points and manageability inflection points, and you just you break, let's say, those into different domains, and in order to, let's say, to accommodate those scaling mechanisms. If I don't hit that scaling area, maybe I just don't need to re-architect, right? So I can be really fast deploying something on relational databases and have it for the next 10 years. If my application starts to, let's say, slow down, then I need to do re-architecture. And I'm a big fan of working in that direction. So working requirements based and not working, let's say, cool technology based, because that really doesn't help my business. And in the end, it's not stopping here, right? So it's a feedback loop. Once you maybe split up and you implement your application, do the process again. So look at your transaction per second. They are increased transaction per second, but how many transactions per second can I have until I hit again the latency point, right? Maybe if I hit the latency of, let's say, more than 50 milliseconds or 100 milliseconds response time, that will be the next scalability point, inflection point, right? The same with throttling errors or transactions, or at which rate, that's also an important question, at which rate the price changes that I put in DynamoDB, I can see the replication delay into the search. That may be also a problem in the future. So I need to optimize that transfer of data to the search, so I don't put in the search results that are already outdated, for instance, right? Yeah, and how much does it cost? So at the end, I moved maybe to hundreds of microservices, even if I only need like 3. It will cost maybe a lot more to do that, let's say, early optimization, instead of just going and looking maybe to use my current architecture and technology until maybe I hit like 70, 80% of my scalability capability, right? So when do I when do I start seeing contention, right? So that's how many transactions per second. I see already like waiting times for transactions. And this is only like I said, it's a process of feedback, of improving. The same will happen, at least if you look into the news last year, you may saw a lot of generative AI application, right? So thinking about Gen AI application, behind the scenes, it's the same thing. So there are a lot of foundation models, a lot of analytics, a lot of databases, data storage, data integration mechanisms that happens behind the scenes. If you plan to do also a Gen AI application, which needs to be also maybe data intensive, you can look again at the same process, right? So for instance, if you want to do a contextual prompt engineering, right? So if you want to do just prompt engineering, I'm just hitting a generative AI model, then there are some data stores in your application that you need still to use. So think about in-memory cache. You want to keep in cache in memory, for instance, the conversation history or the session history. So all this kind of stuff, you don't just put in a relational database. You can take it out into an in-memory database. Another thing is maybe you have a conversational state or history that you really need to get over ID. This is like get conversation ID. That would be a good fit, for instance, for a DynamoDB table. Or anyway, if you have Gen AI application which also need data storage, the process still applies, right? The same thing if you don't do only prompt engineering, but you are thinking more doing like RAG, so retrieval augmented generation, you may need a vector database somewhere where you store your embeddings, right? So think about this area here. That will be maybe your I don't know, maybe you have a relation database like a Postgres that has PG vector extension, may do the trick. See when the trick is not going to be fulfilled anymore. At some point, maybe you need number of embeddings per second. When does my database does not scale anymore? Maybe move to an open search afterwards, or maybe just buy another software that can run vector databases. If you really hit that scale in the number of transactions per second in your application. Great. I hope you learned something new today from how to you architect and design for data intensive workloads. I want to thank you, and looking for maybe for the next 5 minutes to do some questions, looking in the chat. And yeah, if not, then wish you a great JCon World Online conference from here on. And if you want to reach out, you see my Twitter or my LinkedIn. Actually, I challenge you, if you can just if you're seeing this talk, just write me on LinkedIn. Say, hi, I saw your talk. This is what I think about your talk. And let's keep in touch if you have also questions afterwards.